Jai Hind to all. My name is Manoj Kumar, Assistant Professor, Department of Computer Science and Engineering, Akgec Engineering College, Ghaziabad. Today, in this video lecture, we will learn about the swapping and paging in memory management in context to the operating system. So, this is the table of content. First, I will explain the concept of the swapping, what is swapping and how does swapping work. And after that, paging, what is paging technique and what is the concept of the paging technique. So, let's start with the swapping. Actually, swapping is a process in which the pages can be swapped out from main memory to secondary memory and from secondary memory to main memory. And actually, there is a scheduler which is known as the long-term scheduler, which is known as the mid-term scheduler, and mid-term scheduler is basically responsible for this particular task swapping. Actually, in paging technique, whatever we do, this concept is generally used in case of paging technique. This is the basic diagram for the swapping concept. This is our main memory and this is the secondary storage. Initially, there are two processes of program on the secondary storage, pros P1 and P2. And this is our main memory. Program are loaded in this user space. User program are loaded in this user space. So, what happen whenever, suppose, initially, first program P1 is loaded into main memory. P1 was in main memory. And next program is our P2. Okay. So, suppose after loading the program P1 into main memory, our main memory space is full. Main memory is filled now completely. So, now we have to execute the program or process P2. And since in order to execute the process P2, it is necessary that this process P2 must be available in main memory so that CPU can fetch the instruction from main memory. Okay. But in order to load the process P2 into main memory, there is no memory space available. Okay. What is the situation? Situation is that there was a program in main memory, which is the program P1, and now we have to execute the program, another program of process P2. So, we have to load this process P2 into main memory. What is happening? There is no space to load P2 in main memory. So, what we will do now? In that case, we have to make the space free from this process P1. So, what we will do, or what the mid-term scheduler will do, that will remove this process from main memory and send this to the secondary storage. Okay. So, this operation is known as the swap out. Swap out is a operation of swapping process, and during the swap out, a particular program or particular page is moved from main memory to the secondary memory. And another operation is swap in. Swap in is also a operation of swapping process, and in swap in operation, the new process or new pages will be moved from secondary storage to main memory. Okay. So, this swapping process is a combination of two operations. First is the swap out and second is the swap in. In case of swap out, a particular process or pages is moved from main memory to secondary storage, and in case of swap in, the process is moved from secondary storage to main memory. Okay. So, this is the basic concept of the swapping process, and swapping is basically generally performed when we have to load the new program or new pages into main memory, but there is no memory space available to load that particular process or program. In that case, we will make the space free from the existing process, available process in main memory. We will move that process to secondary storage, swap out from main memory, okay, and brings the new process into the main memory. So, this process of moving the process or pages from main memory to secondary memory and secondary memory to main memory is known as the swapping. So, swapping is a process of moving the pages or process from main memory to secondary and secondary to main memory, and this is performed by the help of two operations, swap in and the swap out. Next one is the paging. What is paging technique? Actually, paging technique is a non-contiguous memory management method. Actually, what happened in case of contiguous memory management method, there were two problems of internal fragmentation and external fragmentation. Due to the problem of internal fragmentation and external fragmentation, some memory space was wasted. It means the memory space are available in a scattered manner, but we cannot use that memory space to allocate any new program or new process. So that was the problem with fragmentation. So in case of paging technique, we remove the fragmentation problem. Okay, if our memory space is available in a scattered manner or in non-contiguous fashion, then we are also able to allocate that memory space to the process. So if memory space is available in non-contiguous manner, then paging technique can be used to allocate or to utilize that memory space. So in paging technique, what is the basic concept? This is the diagram of the paging technique. There are two memory. First one is the logical memory. Logical memory is nothing, it is the process size on the secondary storage. This logical memory is corresponding to the secondary storage in context to the program size or process size. And this is our main memory, also known as the physical memory. So what is the basic concept of paging technique? We divide the logical memory into equal size of partition, and each partition of that logical memory is known as the page. Okay, and similarly we divide the main memory, operating system divide the main memory into equal size of part, and each partition is known as the frame, and this partition is known as page. What is the main concept here? Main concept in the paging technique is that size of page must be equal to the frame size. It means page size should be equal to the frame size. Suppose if page size is 4 KB, then our frame size should also be of 4 KB. This is the basic condition of the paging technique. So in case of paging technique, operating system divide the logical memory into equal size of partition, and each partition is known as the page, and main memory is divided into equal partition. Each partition is known as the frame, and this partition is carried out in such a way that page size must be equal to frame size, because this frame is used to hold the page. It means we will allocate the memory space to page in the frame. Okay, so suppose our and this is another one, third entity, which is known as the page table. Page table is basically act as a data structure which contains the information about the page and frame. It means which pages of logical memory is loaded or stored in which frame. That information is available in page table, and memory space to the page table itself is allocated in main memory. It means this page table must also be stored in main memory. Address space of this page table is allocated from the main memory, and this page table contains the information that which page is loaded into which frame. For example, here in our logical memory, we have divided into 4 parts. So there are 4 pages, numbering started from page 0, page 1, page 2 and page 3. And main memory is divided into 8 partitions. It means there are 8 frames in main memory, numbering started from 0. So frame 0, frame 1, frame 2, frame 3, frame 4, frame 5, frame 6 and frame 7. Now this page 0 is loaded into frame 1, page 1 is loaded into frame 4, and page 2 is loaded into frame number 3, and page 3 is loaded into frame number 7. So once we load the pages into frame, then we need to update the page table. Okay, so page 0 is loaded into 1. So this part is known as this column is known as the page number, and this column is known as the frame number. Okay, so we, after loading the page into main memory, we have to update the page table. This is another example, but what is the main concept? Whenever CPU required the data from any pages, then CPU will generate the logical address. Suppose some instructions are written in page 0, some instructions are written in page 1, page 2 and page 3. So whenever CPU want to fetch the data of page 0, page 1, page 2, page 3, then CPU will generate a logical address. So logical address is an address generated by the CPU, and that logical address is basically divided into two parts. First part is known as the page number, and second part is known as the page offset. Okay. So whenever CPU want to fetch the instruction from any of these pages, then CPU will generate the logical address, and that logical address will contain two parts. First part will be the page number, second part will be the page offset. Page number represent the page number value, and offset basically represent the index or location of the instruction in corresponding to a specific page number. Okay. Now our task is to find the physical address corresponding to this logical address, and this is performed by the memory management unit. Okay. So CPU will generate the logical address. Our task in paging technique is to find the physical address. So what will be the physical address corresponding to the logical address generated by the CPU? Why? Because the actual instruction will be stored in main memory. Whenever CPU interact with the main memory, and whenever the page is loaded into main memory, then at which particular physical address that particular instruction is stored. So it is necessary to know the page address, physical address. So once the physical address is known, CPU will fetch that particular instruction from the physical address. So suppose this is a concept of finding the logical address, finding the physical address corresponding to a given logical address. Suppose this is our logical memory, and size of logical memory is 16 byte. Okay. We have divided in logical memory in 4 pages. This is our page 0. This is page 1, page 2, and page 3. And page size is here. Page size is 4 byte. Okay. So starting 4 byte, 0, 1, 2, and 3 belong to page 0. 4, 5, 6, 7, page 1. 8, 9, 10, 11, page 2. 12, 13, 14, 15, page 3. It means each and every page consists of 4 byte here. So this is the offset or indexing corresponding to the pages. So this index 0, 1, 2, and 3 in context to page 0. Again, this indexing is corresponding to the logical memory, but in context to this particular page, this will be 0, this will be 1, this will be 2, this will be 3. It means this is the first byte, this is the second byte, this is the third, this is the fourth. Again, this numbering is corresponding to whole logical memory, but in context to this particular page P2, this will be 0, this will be 1, this will be 2, this will be 3. Similarly, this numbering is corresponding to whole logical memory, but in context to this page, this will be 0, this will be 1, this will be 2, and this will be 3. Okay. Now, this is our main memory. Size of main memory is 32 byte. And we have divided main memory into 8 frame. Because page size is 4 byte, so for 32 divided by 4, it means 8 frame. There will be the 8 frame in main memory. Clear? Now, what we will do, we loaded these pages into frame number. This is our frame number 0. This is frame 1, 2, 3, 4, 5, 6, and 7. So page number 0 is loaded into frame number 5 here. Okay. And page number 1 is loaded into 6. Page number 2 is loaded into 1, frame number 1, and page number 3 is loaded into frame number 2. So, for example, now we are going to find the physical address corresponding to a logical address. Suppose CPU generated a logical address 0111. This is our logical address. Now, we will divide it into two parts, physical page number and the page offset. So, how many pages are there in logical memory? 4 pages. So, how many bits are required to represent the page? 4 equal to 2 to the power 2. So, 2 bits are required to represent the page. So, page number, this will be the value of page number. And this is the value of offset. It means CPU want to access the information or instruction stored inside the page number 1 at the index 1 1. It means this is 0, this is 0 1, this is 1 0, this is 1 1, again this is 0, this is 0 1, this is 1 0, and this is 1 1. So CPU actually want to fetch this H if the logical address is this. Now we have to find the physical address. So what we will do? We will see the page table. It means this page number 1 is stored in which frame number. So from page table we have find that this page number 1 is loaded into frame number 6. It means frame number 6 here. Okay. So in order to obtain the physical address, again physical address will be divided into two parts. First part is known as the frame number and second part is known as the frame offset. Okay. So since there are 32 bytes in main memory, so physical address, how many bits will be there in physical address? 5, because 2 to the power 5 is equal to 32. So physical address will be of 5 bit. Now, since the size of frame is equal to the size of page, so 2 bits are required to in page offset. Similarly, 2 bits are required for the frame offset, because how many index will be there in pages and same number of index will be there in a particular frame. So this part, last 2 bit will be required for the offset and value will be same. So this will be 1 1. Now the page number 1 is loaded. This part belongs to the frame number, belongs to frame 6, and how the 6 is written in 3 bit? 1 1 0. Okay. So our physical address will be 11011. If the logical address is 0111, then physical address will be 1101. And how many 1101 is 16 plus 8 24 plus 3 27. Okay. Now see here, this is 20, this is 24, this is 25, this is 26, this is 27. So we have to find the physical address of H. Logical address of H is 7 and physical address of S is what? 27. Again, let us see here. H is stored at the physical address 27. So in this way, we will obtain the physical address corresponding to the logical address generated by the CPU in case of paging technique. Okay. Again, same thing I have explained. Logical address is divided into page number and page offset field. This is the address translation scheme. The concept I have explained here. CPU will generate the logical address. It will divide it into two parts, page number and page offset. This is the physical address. It will divide it into two parts, frame number and frame offset. So whenever a logical address is generated by the CPU, then at first we will find the entry of that page number into the page table, and from this page table we are able to obtain the information about the frame number. It means this page is loaded into which frame, so frame number is obtained, and this value will be same because size of page is equal to the size of frame. So value of D in case of logical address and value of D in case of physical address will be same. Okay. So once the frame number is obtained, then we can easily find out the physical address, and once the physical address is known to the CPU, then it will fetch the instruction stored at that physical address from the main memory. So in this way the paging technique works. This is page table is a data structure. As I already told that page table contain the information about the pages and frame, and this memory space to page table is itself allocated from the main memory. This is a page table base register which point to the page table. Page table length register indicate the size of page table. It means how many entries are there in the page table, how many pages entries are there in the page table. In this scheme, every data instruction access required two memory access, one for the page table and one for the data instruction. It means at first, in order to know that the page number is stored in which frame, we have to access the page table, and page table is stored in main memory. So one access is required for the page table, and when the physical address is known, Then after that we have to fetch the data. So for that particular purpose, this. So there are two references for accessing the main memory here in order to access the instruction. And sometime there is a use of TLB, which is known as the translation look aside buffer, and it is a type of associative memory, and it also used with the paging technique. So associative memory, this is the concept of paging hardware with TLB. What happen? Sometimes CPU refer the same logical address again and again. Okay. So whenever the CPU want the instruction of some frequently accessed logical address again and again, so since the time taken to access the main memory is more as compared to time taken to access the cache memory or associative memory. So what we will do, those address for which CPU submitting the request again and again, we will store those address in a separate associative memory. So this is associative memory is known as the TLB, translation look aside buffer. It is a cache memory, and time taken to search the TLB or time taken to access the TLB is small as compared to time taken to access the main memory or page table. So for those, suppose there are 100 logical address, and among 100 logical address, 10 logical address are there which are frequently referred by the CPU. So for those 10 address, we will store the information in a separate TLB. Because to access the TLB, it will take the less time. So in order to make the accessing process efficient or fast, what we will do, we will maintain a separate TLB with the paging technique. So what happened now, how this diagram is working, whenever the CPU logical address is generated, whenever a logical address is generated by the CPU, then at first we will find the entry of page number into TLB, whether that page number entry is available in TLB or not. If page table number is entry is available in this TLB, then this is known as the TLB hit. In this case, in the case of TLB hit, there is no need to access the page table because entry of page number and corresponding frame number is available in TLB. Okay, and from TLB frame number we will found, and once the frame number is found, physical address is obtained, and once the physical address is obtained, then instruction will be fetched from the main memory. So in this case, when TLB hit happened or occurred, there will be one access to TLB and one access to main memory. But there may be a second case. Whenever the page number generated by the logical address or generated by the CPU, that page number entry is not available in TLB, then this is known as the TLB base. Now, in order to obtain the physical address, what we will do? We have to access the page table. And where the page table is stored? Page table is stored in main memory. So, first we access TLB. After that, we access the page table, and page table contains the entry of all the pages. So from here, we will get the frame number. Once the frame number is obtained, we can easily find the physical address. When the physical address is known, then instruction is stored at that physical address will be available to the CPU. So in this case, in case of TLB miss, there will be three access. First access will be of TLB, whether the entry is present or not. If not present, in order to know that, we have to access the TLB. Second access is for the page table, and since page table is stored in main memory, so this is a access to the main memory. After that, when the physical address is known, then in order to access or retrieve the data or instruction is stored at that physical address, we need to access the main memory. So in case of TLB hit, there are two access for the main memory and one access to the TLB. So for this diagram, there is a term which is known as the effective memory access time. So we will calculate the effective memory access time in this way. This through this formula. This part is for TLB hit and this part is for TLB miss. And by combining these two, this is the effective average access time. Okay. So H is the hit ratio. Suppose if the CPU generated the logical address 10 times and 7 times there is TLB hit and 3 times is TLB miss, then hit ratio value of H will be 0.7 or 70% hit ratio. If the entry of page table, page number generated by the CPU is available in TLB and it is available at the 7 time, suppose 10 references are generated by the CPU and 7 time entry was found in TLB, then hit ratio is 70%. So H plus TAMA is the time required to access the associative memory or TLB, plus TMA time required to access the main memory. Okay. So in case of TLB hit, 1 access required for the TLB or associative memory, 1 access required for the main memory. But this is 1 minus H. It means in case of miss, what will be the miss? 10 minus 7, 3. So, okay, or you can say that 1 minus 0.7, 0.3. Okay, so in this case, 1 access required for the associative memory or TLB and 2 access are required for the main memory. So, by putting the value of associative memory access time and main memory access time and value of hit ratio, we can easily obtain the effective memory access time. Okay, thanks. So, in this lecture, we have discussed about the swapping process, how the swapping works. After that, paging technique, concept of paging technique, how we obtain the physical address in case of paging technique. This is the address translation scheme from logical address to the physical address. Next, we have shown about the TLB, how the paging technique work with the TLB, or TLB is a kind of associative memory. Okay, and how we calculate the effective memory access time. Okay, thank you.